Hi everyone, today I'll be talking about massively parallel algorithms for small subgraph counting. I'm Quanquan Liu, and this is joint work with Amartya Shankar Biswas, Talia Eden, Slobodan Mitrovic, and Ranit Rubenfeld. I want to start by giving a brief 1-minute motivation for why we are interested in this problem. The massively parallel computation model, or the MPC model, is a model used to theoretically study algorithms operating in parallel frameworks. With the growing popularity of frameworks and programming models such as MapReduce, Hadoop, Spark, and Dryad that distribute computation across many machines and then perform such computation in parallel, the MPC model has become the theoretical standard for studying algorithms in such massively parallel frameworks. Counting small subgraphs in graphs is a widely studied problem in the sequential, parallel, distributed, sublinear, and streaming domains. In addition to its theoretical importance, small subgraph counting also has a number of applications. In database literature, the triangle counting algorithm is used to perform joins and to analyze the worst-case runtimes of join algorithms. In analyzing the social structures of social networks, small subgraph counting has been used to detect communities and measure the cohesiveness of these communities. Triangle counting even has applications in spam detection. Due to the applications of this problem to large graphs with millions or billions of edges, it seems important to theoretically analyze this problem in the MPC model, which is a model that is meant to handle processing of such large graphs. In the context of triangle counting, in many scenarios, algorithms that perform exact counting are too prohibitive in general graphs. They take up too much time or too much space or both. Approximate counting, on the other hand, oftentimes require less time and space. However, to obtain good estimates on the subgraph count and to provide approximations that concentrate well require lower bounds on the count of the subgraphs in an input graph. Thus, a worthwhile goal is to provide an estimation that concentrates well while imposing as small a lower bound on the actual count as possible. Due to these reasons, it seems important to study both types under different input conditions. There has been a long line of work on small subgraph counting, including some that are very recent, in the sequential CRC PRAM, streaming, and distributed models. Some of these works are listed here. Please refer to our paper for a thorough exposition of the history of these works on this topic. In models similar to the MPC model, Finocchi, and Fusco designed an algorithm for clique counting, which requires O of m to the 3/2 total space. And Affredi, Fotakis, and Ullman count small subgraphs using either superlinear total space or almost O of m space per machine. Suri and Vizovitsky designed two algorithms for exactly counting the number of triangles. Their first algorithm runs in 2 rounds and requires O of square root of m space per machine, and total space O of m to the 3/2. Their second algorithm requires only 1 round using total space O of rho times m and space per machine O of m over rho squared. Therefore, for this algorithm to allow for polynomially less than space m per machine, it has to allow for the total space, which is polynomially larger than m. Chu and Chen present algorithms that require total space O of m, but in the worst case, their algorithm requires O of the number of edges in the graph divided by the space per machine. If the number of edges in the graph is n squared and the space per machine is n, then their algorithm will require O of n rounds. In the domain of approximating triangle counts, 2 independent works design randomized algorithms for obtaining 1 plus epsilon approximations on the triangle count. Their approach sparsifies a graph by sampling a subset of edges for each machine. Then they execute known algorithms for triangle counting on each of these machines. Using their algorithm, given a graph where m equals theta n squared, their algorithm gives a 1 plus epsilon approximation with constant probability of success when t equals omega of n. Pak and Sorakakis present a randomized algorithm for approximate triangle counting based on graph partitioning. Their algorithm partitions a graph into 1/p pieces, where p is at least the ratio of the maximum number of triangles sharing an edge, and t the actual number of triangles in the graph. In the case when all triangles share one edge, p will be greater than or equal to 1, and their algorithm requires the space per machine to be omega of m. Seshardri, Pinar, and Koda design an algorithm that samples wedges and determine whether the wedges form triangles. Their approach requires that t is at least a constant fraction of the sum of the squares of all the degrees. Despite the progress on approximating triangles in the MPC model, and to the best of our knowledge, on one hand, each MPC algorithm for exact triangle counting either requires strictly superlinear in M total space, or the number of rounds is super constant. On the other hand, each algorithm for approximating triangle counting requires t to be greater than or equal to n, even when the space per machine is theta of n. We design an algorithm that has essentially optimal total space O of m, space per machine O of n, and round complexity O of 1, while at least quadratically improving the requirement on n in the approximation case. For the algorithms in our paper, we seek to obtain nearly optimal total space, which is O of m, and nearly optimal round complexity, which is O of 1. For the remainder of this talk, I will focus on explaining the details of these two results shown here. The first result I present is a specific setting of our more general result presented in our paper. To see the more general result, I refer you to our full paper posted on arXiv. I will also briefly mention at the end of my presentation, extending the second result to counting cliques and subgraphs smaller than 5. I will start with the first result. Note that the first result holds when the number of edges is at least the number of vertices. We can ensure this by doing one round of preprocessing where we delete all vertices with no edges. To begin, we first define some terminology relating to the MPC model. There are M machines which communicate with each other in synchronous rounds. The input graph is initially distributed across the machines in some organized way so that machines know how to access the relevant information via communication with other machines. Each machine has S space in words. During each round, each machine first performs computation locally. Each machine can use unbounded computation time, but most reasonable algorithms will only use time that is linear or quadratic to the space of the machine. At the end of each round, the machines exchange messages with each other to inform the computation for the next round. The total messages sent and received by the machine is upper bounded by the space of the machine. We also care about the total space used by all of the machines. By our definitions, we can calculate the total space used to be m times s. I'll give a very high-level overview of our algorithm to start. In short, our algorithm reduces approximate triangle counting to exact triangle counting in multiple induced subgraphs of the original graph. Suppose we have several machines with limited space and given an input graph distributed in some organized way across the machines. Each machine samples some subset of the vertices of the graph by including each vertex in the machine with probability p hat. For simplicity, from now on, I will refer to p hat by p. After sampling vertices into the machines in this way, each machine counts the number of triangles in an induced subgraph in each machine. In contrast to PT12, the induced subgraphs on different machines might overlap. The total number of triangles seen across all the machines is used as an estimator. We repeat this process O of log n times in parallel with only an O of log n factor increase in total space, and then we return the median of the estimates as our final count. There are a number of challenges we must solve with our algorithmic approach described in the previous slide. Our first challenge is that we need to set the sampling probability such that the induced subgraphs in each graph does not exceed the amount of space it has. Even if the subgraphs fit in the machines, we also need to make sure computing the induced subgraph in each machine does not exceed the total allowed space. Finally, we need to show that the number of triangles across the machines concentrates. Recall that each vertex is sampled into a machine with probability p hat. This means that the expected number of triangles in a machine is p squared times m. Suppose that the space per machine is S, we must have that the expected number of edges is less than the space allowed. Thus, p hat must be less than square root of S divided by m. More concretely, we set p to be 1 over 10 times square root of S divided by m and k. I will define k in the following slide. To illustrate challenge 2 more clearly, suppose we define QU to be the set of all machines containing vertex U. Each edge, UV, needs to be sent to the set of all machines containing both U and V. This would be QU intersection QV. Suppose we send both of the sets QU and QV to the machine containing edge UV. Then, each set QU could be replicated degree of U times. By our setting of the probability from the previous slide, the expected size of QU is P times M. Summing over all vertices, this would result in asymptotically greater than linear in M messages for all cases when S is tilde little o of M and K is O of log N. I will show that K is O of log N shortly. Hence, to ensure that the total space is O of M, we need to have a different way to find all induced subgraphs. To solve this challenge, we use a globally known hash function h to determine whether vertex v is sampled in the ith machine. We use this hash function to efficiently compute which edge is sent to which machine. Each machine computes for itself the set of edges that it contains by calling the hash function. Furthermore, the probability the hash function on an input outputs 1 is given by p. We must be mindful that the hash function does not use too much space. Thus, we cannot use a fully independent hash function. Instead, we use a k-wise independent hash function where k equals O of S over log n. In fact, we show that we are able to achieve our approximation guarantees even if we allow as little as 6 log n wise independence. Thus, throughout, we set k to be equal to O of log n. For the third challenge, we must show that the number of triangles across the machines concentrates by taking into account dependencies introduced by our 6 log n wise independent hash function. According to our algorithm, each individual machine performs a single experiment, and then the collection of machines repeats this experiment in parallel across m machines. Any machine which receives more nodes and edges than S gets discarded, and its count does not count towards the total. The sum of the counts of all machines except those that were discarded is multiplied by 1 over p cubed times r, where r is the set of machines that were not discarded. We show that the number of edges sent and received by any machine is at most S with high constant probability. Specifically, we show that this occurs with probability at least 9/10. Then, by performing the sampling process omega of log n times in parallel among 100 omega m machines, it allows us to obtain a 1 plus epsilon approximation with high probability by using the median of means trick. In order for us to provide a 1 plus epsilon approximation of the number of triangles, at least one triangle must be sampled. Since the expected number of triangles in a specific induced graph is p cubed times t, where t is the actual number of triangles in the graph, in order for us to see omega of 1 triangles, we must set t to be large enough such as p cubed times t and m is omega of 1. Since p squared times m is omega of 1 by our setting of p, we only need to show that p times t is omega of 1. Then it suffices to show that t is greater than 1 divided by p. Since we set p to be theta tilde of square root of s over m, this implies that t has to be greater than theta tilde of square root of m over s. Then, when s equals theta of n, t has to be at least square root of m over n, which is equal to the square root of the average degree. Hence, we obtain our stated result, a 1 plus epsilon approximation with high probability if t is greater than or equal to square root of the average degree of the graph when the total space is O tilde of m and there is theta tilde of n space per machine. Now that we've shown our first result, I will explain the second result shown here. We perform exact triangle counting in graphs with bounded arboricity for our second result. There are many important graph families, such as planar graphs, bounded degree graphs, and randomly generated preferential attachment graphs, which exhibit bounded arboricity. In fact, many real-world graphs exhibit bounded arboricity, which makes our algorithm potentially important in practical settings. Our total space complexity matches the time complexity, both the upper and the lower bounds, of the sequential algorithms for exact triangle counting in bounded arboricity graphs. We show how intuitively our algorithm works here. Suppose we are given some graph with arboricity alpha. We start with round I equals 0 and we remove all vertices with degree at most 2 to the 3/2 to the I times 2 alpha. Suppose the blue vertices have degree at most 2 alpha in the first round when I equals 0. We then remove them and count all the triangles incident to them. In this case, there were 2 triangles incident to them. We continue doing this while the degree bound increases doubly exponentially. We continue until there are no nodes left, and our final cumulative count is 5. We immediately see that this procedure takes all of log n rounds if the space per machine is unbounded. However, this is not the case. So given a small s, smaller than, say, the induced subgraph of the neighborhood of a node that is removed, we cannot count all the triangles incident to that vertex on one machine. Instead, we need to have an MPC-specific counting procedure for this problem. To solve this issue, all removed nodes first send its list of neighbors to all its neighbors. Then we use the MPC sorting algorithm of Goodrich et al. To sort all received neighbor lists with the neighbor lists of the receiving vertices. We then find all duplicates in the sorted list using our new MPC primitive. The number of duplicates then gives us the count of the triangles, which directly leads to our second result. which is there exists an MPC algorithm that outputs the exact count of triangles in a graph with arboricity alpha in O of log log n rounds, O of n to the delta space per machine for any delta greater than 0, and O of m alpha total space. We can extend our result obtained in the previous slide to the following results shown on this slide about k-clique counting and counting subgraphs of size at most 5. However, due to the lack of time for this presentation, I encourage you to refer to our paper to see these results. In order to obtain the results, we also use new MPC primitives, which we hope may be useful for others later on. There are a number of open questions that remain following our results. The most interesting one is whether there are other methods for obtaining induced subgraph partitioning with overlaps whose computation does not significantly exceed the total size of the induced subgraphs. Answers to this question could directly lead to better approximation results in the MPC model. Throughout our study, we noticed that our total space bounds often match the time bounds of the sequential algorithms in the sequential model. Is there a clear reason why this is the case? We would be very interested in obtaining a better understanding of the relationship between total space in the MPC model and the running time of similar algorithms in the sequential model. And this is it for the presentation. We, of course, welcome many questions in our Slack channel.